So these are the typical filter. So now this is the correct way of writing Mel Filter Banks. Typically, we use only Mel Filter Banks in today's deep learning based methods, but there are still statistical conventional GMM-HMM, which we'll talk about later, which do very well when we deal with MFCCs. And how do we get to this MFCCs? The full form is Mel-Frequency Cepstral coefficients. We start with the speed signal. There is an idea of emphasis, that is because of spectral runoff. Don't worry, we do that windowing. Remember, I said that speech, it's time varying, right? I mean, I speak different sounds. So we localize information, then we compute the Fourier transform. For Fourier transform, there's an algorithm called the fast Fourier transform. Then we apply the averaging, the Mel filter averaging, the triangular averaging. After we apply the triangular averaging, we are going to apply the log, and usually at this point we stop. This is where we are going to use in most cases in deep learning methods. We don't, in deep learning the correlations actually don't hurt, okay. But if you are doing conventional statistical GMM-HMM kind of methods, we need to do two additional steps, or at least one additional step, which is called the DCT, which will take the log Mel filter bank and produce MFCC. But we also on top of that often use things like delta and delta delta, and I'll talk about it a little later, okay. So I am interested mostly in two things: Mel filter bank, which are nothing but outputs of the filters in the frequency domain. This is frequency domain, and the reason why we do this is that's Mel, okay. So because inspired by ear. Okay, and we normally apply a log on top of this. After this, we do a log operation. Okay, so that is what we typically use for deep as features for deep learning. What are features? So why? So these are what we call as features. What is relevant for a particular problem? So suppose I am designing a trouser or something, right? So I am designing a trouser, right? So this is my trouser. So the waist size is there, right? And then the height is there, right? So height, right? So when I am designing a trouser or something, right? What do I need? I need waist size and height, right? Something like that. So these are useful features. These are features or some measurements that are relevant for my design or for my modeling and so on, right? So similarly, when I'm processing the speech signal to do something useful, I'm going to extract something relevant, and those are what we typically mean by features, correct? So, and where we are interested right now is in the vocal tract information, right? What is the different sounds that are being produced, and that's why we are doing that smoothing, averaging, and by using this triangular averaging and finding out the vocal tract information, okay. Now, there are two ways we can do. We can do the Mel filter bank, and this is called log Mel filter bank, okay. And typically what we need is in the Mel domain, we want equally spaced equal bandwidth. But we are going to do in the physical frequency in hertz. So we know F Mel is nothing but 1125 ln of 1 plus F hertz by 700. So the same thing will appear like, the same thing will appear like this in the physical frequency, okay. These two are equivalent pieces of information. This is the practical way of doing, practical implementation of Mel. Okay, and then what do? We apply a log in the magnitude domain, log in the magnitude direction, the y-axis. Yeah, okay. And so we get log Mel Filter Bank coefficients. Okay. And typically in speech, we use about 40 Mel Filter Bank when we are talking about telephone speech, which has a bandwidth only of 4 kilohertz, and about 80 Mel Filter Bank when you are talking about wideband speech. Okay. So, do you remember what is telephone speech and wideband speech? The telephone channel cuts off everything beyond 3.6, 3.7 hertz, kilohertz, and therefore, sampling frequency should be twice that, around 7.6, 7.8. So, these are sampled at 8 kilohertz, right? And these are sampled at 16 kilohertz, because typically the frequencies, when we speak, we don't produce anything beyond about 7.5 kilohertz, maximum 7.6, so, in that ballpark, right? 7.2 to 7.6 kind of kilohertz is what we produce, and therefore twice of that is about 16 kilohertz. So, obviously, we have doubled it, so we also use the double the number of filters. Okay, and so typically when you are talking about deep learning methods, right? So deep learning kind of methods, you will use these 80 log Mel Filter Bank outputs. Mel Filter Bank outputs as features. So, what do I mean by that? I am going to take a speech signal, right? So, this is speech signal, and it's all short time processing. So, I am going to take a window of 25 milliseconds. This is 25 milliseconds. I am going to take an overlap of 10 milliseconds. So, this is again 25 milliseconds. This is again 25 milliseconds, right? And this is again 25 milliseconds. Remember, when I talked about the window in the spectrogram, I already mentioned that we use typically about 25 milliseconds. That has been found out to work best. Again, all of these are experimental. They have been empirically found. And here there is 10 millisecond before the next thing starts. Again, this is 10 millisecond. Again, this is 10 milliseconds. So every 10 millisecond, I'm I'm moving it in installments of 10 milliseconds. The window remains 25 milliseconds. Okay. So now every 25 millisecond, what do I do? So let me go back here, right? So I take the first 25 milliseconds. So whatever it is, like this, right? So now I am taking the first 25 milliseconds, right? So this is my 25 milliseconds. Okay. What do I do? This is a time domain signal. Remember, this is time, right? There is an operation called pre-emphasis. Let me not talk about it. I want to first go into the frequency domain. So, I go into the frequency domain, and for doing that, we need to do Fourier transform, right? Basically, some kind of a transform to go into the frequency. So, we use DFT. And typically, this is implemented using a fast Fourier transform algorithm, right? After that, we come into the frequency domain. So, this is now in the frequency domain. Now, this is actually S of omega. Then I am applying, this is S of t. So, this is S of omega. This is my frequency domain, right? Then what am I doing? I am first of all taking only magnitude. So, it will be this guy, magnitude, right? But remember that I want to apply some kind of a liftering process. I mean, I want to smooth it out, right? So, that is why I am going to do a log operation on that. So, and basically to separate out the two things, and then to remove out the effects of the excitation, I am going to do some kind of a triangle filtering, right. So now I want on top of this, this is going to be some kind of a, whatever it is actually magnitude that I am talking about. These are the frequency domain curve. So it will be something like this is the envelope, right, and then the pitch harmonics are coming, right. I am going to do now a triangular filtering. So this one will be this. This is the triangular Mel filter. It's actually filtering, but it's Mel filter by triangular averaging. That's what I'm saying, but this is called Mel filtering. Then I'm going to take the log of it. So then I have the log of this outputs that I get. Now these are the outputs. So these numbers that I get, right? So these are the numbers. So these numbers. I mean, after averaging, not the peak. After averaging, I'll get maybe I should put a different value here. So here some number will come. That log I'm going to it is going to come like this, and the log will take care of it. Okay. So this is where I can stop. There will be 80 such values, right. So I'll get 80 such outputs. For 16 kilohertz or 40 if I am using 8 kilohertz. So this one is called 40 Mel log Mel filter bank outputs or 80 log Mel filter bank outputs. Correct? So this is for what? 125 millisecond, right? So I have to do this for now every. So this one I can plot it as one big vector. So 40 dimensional vector or 80 dimensional vector. This is the feature vector Mel filter bank feature vector for first 25 milliseconds, right. So or 80, whichever one of the two. So now I'll redraw that so that it becomes clear. So you will get a sequence of vectors. So just to remind you, so I have some speed signal, right. I am going to have some speed signal, correct. And what am I going to do? I am going to do this 25 millisecond window, right, another 25 millisecond window, another 25 millisecond window, and each of these are separated by 10 milliseconds, 10 milliseconds, right. So on, and the fourth one I can start here maybe, again 10 milliseconds, right. So the red one will produce one vector which is, let us say, 80 cross 1, okay. So this is for the first 10 milliseconds. Then by doing these operations, right. So I did this now. I took the first 25 milliseconds, took the DFT, then applied the triangular filtering, and then I did this, right. So I will get something like this. Then the next blue one will give me another feature vector, again 80 cross 1. The green one will give me another vector, which is like this green one will produce another vector, and then the black one will produce another vector, and so on. So I get 80 cross 1 vectors every 10 milliseconds. log Mel filter bank features every 10 milliseconds. That's what we are going to do. So, this is a long time I am going to be producing a sequence of features, right. So, it is a sequence of features. So, we are going to get a sequence, and this idea is very, very important. So, we are going to get sequence one after the other. There is a relationship, first this came, then this came, then this came. There is a time ordering, right. So, there is a time ordering, right. The order in which these features appear, right, are important, right. They are following one after the other, each is capturing some information. So, the order in which the sounds are produced are very important, right. So, if I am writing also, I can't jumble the characters, then I will not make words, right. Each word has the characters or the alphabets written in a particular way, right. If I want to say get, I have to have first G followed by E followed by T, right. I cannot put E, G, T, any, or that is not the word get, right. It forms another word then, right. So, therefore, this ordering, the order in which they appear becomes very, very important, and there is a whole class of the deep learning methods where we worry about this order. So, we call about sequence based, sequence to sequence methods and so on. Okay. So, the sequence information is very important in many applications, and the idea of sequence itself, that is why we have time series analysis. So, the order in which they appear is also very, very important. It is also used in predicting, right. So, whether stock market and so many things. So, this time ordering is always a very, very important aspect. Okay. So, this is what we normally stop nowadays, right, because this is what we mean by Mel filter bank features. Okay. But if you want to use a conventional statistical based methods like GMM-HMM and so on, right, then we are interested in having decorrelated features. Okay. So, for example, GMM, often the assumption, I will come to, you remember this, I will come to this idea, it will become a little more clearer later. Okay. So, do not worry too much about what is this. If you are not read, you can just revise from your, some of the math courses you might have done before this particular course, but there is an assumption of diagonal covariances, and so some idea of uncorrelatedness is important. For Gaussian, of course, we can argue that independence and uncorrelatedness are same, but generally, let us say we are interested in decorrelating or uncorrelating these features. And as I said, the way to think of it is, it is some kind of a Gram-Schmidt, like how we orthogonalize vectors. Here we are, the variables are made, not independent, I mean depends on the assumptions, but at least they are made to be uncorrelated with each other. Okay. So, therefore, what do? We in the decorrelating something, we have computed something called the covariance matrix, and then use Cholesky decomposition and do lots of pre-whitening kind of operations. I am not going to talk about all of this, but in speech there is a very simple method, and what we do is, for speech we take the log Mel filter bank, which are typically correlated features, because the reason why they are correlated is there is a lot of overlap between these guys, and also the frequency content changes slowly, right. I mean, so it is not, there is a high degree of correlation between adjacent samples. So, what we do is take the log Mel filter bank and apply something called DCT2, okay, which is a discrete cosine transform. There are many versions of it. So, the discrete cosine transform, and there are 16 actually, you can look at it, okay, but at least 8 are there. So, we are taking the second variation of it, and DCT2, and then we get what we call as the Mel-Frequency Cepstral coefficient, and often this term MFCC will be used. Okay. And no, typically these are 40 or 80 if you remember. Okay. And what happens in Mel filter Cepstral coefficients is we retain, this is again we are retaining the low pass part of it. So, we retain only the first 13. Now, why did we arrive at 13? Why not 15? Why not 10? Again, this is empirical, right? I mean, historically, people have used 13 Cepstral coefficient, 12 plus energy, or 13, C naught plus C1 to C12. So initially people somehow got stuck with this idea of 13, right? And we are stuck with that. And there's some reason why we don't want to go to too high or too low. Okay, too high, we'll start getting the pitch effects. Okay, but whether it's 13, 12, 14, 15, I don't think it will make much of a difference. There will be some performance gains or performance degradation depending on the application, okay, and the signal, and many aspects of how the data was collected. But we typically use 13 Mel-Frequency Cepstral coefficients, okay. And so in MFCC, every 10 milliseconds we get 13 cross 1. So this is 13 cross 1, the red one will come, because remember, we took these guys, right? We are going to take these guys and then apply DCT2 here. That's the whole idea, okay. And so you will get that first, and then you will get this 13 cross 1, then you will get this 13 cross 1, this, so instead of 80 cross 1 or 40 cross 1, we will start getting 13 cross 1, okay. And this is called static MFCC. This is called static MFCC. And then we have static coefficients. Then we have something called delta and delta. So this is called delta and delta. And the basic idea is this is like a difference between adjacent we don't use difference, it's a noisy, but the basic idea is difference and the difference of difference, okay. Okay, and so this one is like a difference between the red and the blue, and then the blue and the green, and the green and the black. That's a kind of approximate operation we want to do, but we do it much more intelligent, do it intelligently, okay. So that we, when you do just pure differencing, it's a high pass filter, right? So you have to be a little more careful. So you will get now some kind of a I'll put here, this is the difference and this is the delta, sorry, this is the delta, and then you will get this one, and then you will get the delta, which is some kind of a vector like this. So slightly different, okay, and something like this. So this will be 13 cross 1, and this will be 13 cross 1, and so we concatenate all of this, and then we get concatenate and get 39 cross 1. Sorry. MFCC vectors, okay, and that is used in mostly your GMM-HMM kind of methods, okay. So I will stop here, and next class onwards I will start with what is a Gaussian, why is it useful, right, and then what is a mixture of Gaussians, and then we will slowly go towards Markov models and then hidden Markov models, okay. So I will stop here. Thank you very much.